monodromy relations in string theory from twisted homology.
Thank you for inviting me. It's my first time here. It's very nice, very welcome. So what I'm going to talk about, and I'm going to explain how this terms, what they are in detail. This is work that I've been doing with Piotr Turkin and Sebastian Gizera. It just appeared a couple of weeks ago. And we've been thinking about these things for some time. And this is the first paper we have on this, but there's some ideas here that we want to push it forward. But this is already some nice, interesting results where we can rewrite and understand what these things are, these moduli relations, which were known in the string theory for quite some time, since the 80s and 70s, in some new language. And then using that, we can generalize further. So the summary, basically, of the ideas is that there's a shown by Gizera quite recently the string theory, well, three-level string theory amplitudes. By three-level, I mean word sheet is just a sphere. There is an interesting interpretation of these amplitudes in terms of what is called twisted cohomology and twisted homology, which I will explain later. And when on the moduli space, so this is the moduli space of n-punctured spheres, so genus 0 and n-punctures. And what this does to you, it does a very nice geometrization of some properties that before were actually a bit harder to calculate by hand, but using this formalism, we can understand them in these geometrical ways, and we can derive them quite easily. And in particular, what are called monodromy relations, which I'll review in a second, and is the main, really, what I'm going to talk about, and the KLT construction, which I'll also review quickly, and it's something we are still working towards generalizing that. And in particular, these things were really known for the three-level amplitudes, so just sphere worksheets. And what we wanted to do is, for own reasons that I'll explain why we're interested in them, but we wanted to generalize these things for higher loops. In string theory, higher loops means higher genus surfaces. So we wanted to generalize this framework that Sebastian set up for the three-level string to strings defined on higher genus surfaces. And we've been somewhat successful yet to do that with some caveats, which I can explain later on. And so, but once doing that, we wanted to see, because this is the first time we're setting up this formalism, we want to make sure that we are doing this correctly. So we use that to rederive this monodromy relation at three-level and some, but we also do for any genus, and we compare to some results in the literature. And what is in the literature is the three-level relations and some low genus results, some very specific low genus results that we can reproduce. And actually, we can solve some discrepancy on the literature at that point, which I'll also come to later. And also, these relations also give some, in the field theory, they give some nice relations for field theory amplitudes, which is related to double copy and color kinematic duality, which I'll also explain a little bit why and why you're interested in them further on. So most of this talk is going to be a review on this string theory amplitudes, this interpretation of this relation in terms of this twisted homology, introduction, very heuristic introduction to this twisted homology, and then generalization of this to higher genus, which is the main topic of the paper. And if there's any questions at any point, just stop me. So first, I'm going to talk about open strings amplitudes. So this is a three-level open string. Is just a worksheet which is just a circle. You put particles on the boundary. So in green, I denote to the boundary. There's some ordering for those particles that you put 1 to n. This represents the insertions of the vertex operators, which have this generic form. There's some post piece, some matter piece that depends on the theory. There's a universal piece, which is the plane wave piece that comes, any string theory is going to have this flat space. It's going to have any vertex operator for a physical state is going to have this plane wave piece. And it's the piece we're going to focus on. And in particular, that's because that plane wave piece gives rise to this piece of the correlator, which is called the Copenhagen factor. Everything else just goes into producing this measure and producing this function, which is some rational function on the z's, and some linear function on the polarizations, and some function on the momentum. So this is theory dependent, but as a function on the moduli space, it is just rational, so it doesn't have any branch cuts. While any branch cuts might come from this one, because this generically is not an integer. So once I analytically continue this function, then it will produce some branch cuts, and that's the universal part of the string. Right. So because this is an open string, there's also some choice of counter, which is just some choice of ordering and how I order my points on this around this circle here. So monodromy relations then are relations between those amplitudes that I just wrote down. They are written in this form. So here I denoted the ordering of the amplitudes. This is just the ordering of the particles around that circle. And you see that as one goes through these particles, and I lost So what I was saying is that as one goes around, it picks up phases, plus and minus, and this phase for K1, K2, just because it goes around 2, it picks up the phase, and goes on and on and on until it gets to the right before the last one, picks almost all the phases, and then the claim is that the sum of these amplitudes weighted by those phases is 0. Thank you.
Can you remind us where this comes from?
Yes, so the way to derive this is really by it's by doing counter deformations on the moduli space, and I'll come back to this point and how they do this. And
is there a way to state it qualitatively as a property of the correlation function for vertex operators? If you give you, after all, this is what it is, right? This A, is it? Yeah. I give you vertex operators and I compute their correlation.
Yeah, so yeah, so from here, so yeah, basically what happens, and I'll come back to this, but basically what happens, this has to do with this cycle that appears when you exchange vertex operators between each other. They pick up a phase. But it's not only that, because it has to do also, it's an interplay between this what happens with the vertex operator here, but also the counters that are integrating over. Because each amplitude, when one moves around, then you have different counters on the moduli space you're integrating this over. So it's not only the vertex operator, but you also have to make sure that you're doing it to understand how the counters relate to each other. So it's really it's a property of everything, right? And that's where the twisted homology is going to come on, is because the way that this result was derived, just getting a bit ahead of myself, is by doing just naive counter deformations and trying to avoid any branch cuts. And what we're going to use this is we're going to set up this homology theory where you can do this counter deformations crossing branch cuts without having to worry about branch cuts, which basically amounts to you have to set up an homology that knows about this co-inducing factor, that knows about this factor here, so it knows about the OPs basically. So I'll get to that in a second. So these are three. Okay, so this is valid really for 3-level amplitudes. Once you take those two relations into account, plus all permutations of particles, so not only by permitting all these particles inside here, you can give a proof, or a physicist proof, that there are n-3 factorial independent A, so the basis of an independent amplitude is n-3 factorial. And the other thing is that once you take the field theory limit of these relations, you recover some field theory relations, which is the part of the coupling, and what are called BCJ identities, which were actually found before people knew that they came from the string. They were found independently in the field theory, and they BCJ realized that also in field theory they gave n-3 independent gauge theory amplitudes out of that. And then it was only later on that these people realized that they are related by that.
And what is field theory really mean?
So the field theory limit here is going to be is when the worksheet degenerates. So let's say I have 4 points. I have 4 points in a string theory amplitude. When I take the field theory limit, this worksheet degenerates into 3-variant graphs. So there's 3. So this gives 3 different contributions, which is going to be the worksheet degenerating something like this, and something like this, where this is getting very, very, very tiny until it gives a contribution that looks just like a field theory diagram. So these guys sit at the boundary of the moduli space. So taking the field theory limit really means to take the low energy limit on these amplitudes and see what you get in terms of low-power field theory. And what you get is like each term there actually becomes a very complicated sum of 3-variant graphs out of this.
Thank you.
Okay. So the other thing we're going to talk a little bit is just KLT. Talk a little bit KLT. I'm just going to mention what is closed string amplitude. So closed string amplitude then is defined in worksheets which use a sphere. So it's a closed sphere, and you put a bunch of points. There's no particular ordering for these points. And the interesting fact is that the closed string vertex operator has a form that heuristically looks like the square of the open string vertex operator. This is not literally true, but it's almost true. It's true in some theories. But it is it's morally true that this is true. And what I mean by that is that a closed string amplitude then is going to be denoted. Now this is the closed string moduli space, so there's no choice of cycle here. We're just integrating over the whole space. There's a choice of compactification, but that doesn't matter here. And this is again some rational functions of z and z bar. Depends again on some external kinematics. And it's so external momenta and polarizations. But it's just some rational functions on z and z bar. Well, again, you have this Copenhagen factor that comes with a mod and comes with a chu. So that chu is basically what's saying that it's the square, in some sense, the square of the closed string amplitude. And you can make this statement precise, and that's what KLT did. So KawaiLewellen-Tye, quite some years ago, they showed that a closed string amplitude, so on the sphere, can be written as some bilinear on the open string amplitudes, which is true here. So beta and gamma are some permutation. Remember that around that circle on the boundary I have some permutations. So here I have to do some particular sum over permutations for those two. And there's some matrix between them that depends on those two permutations. This matrix is known as KLT matrix. It is an n by 3 factorial, n by 3 factorial, because we know that because of the monodromy relations, there are n minus 3 factorial independent amplitudes like this. And just to give some concrete examples, so for 3 points, it is literally the gravitational amplitude, the closed string amplitude, which gives you a gravitational amplitude, is the square of the Young-Mills amplitude of the open string theory. Once I go to higher points, for example, 4 points, if I pick, this of course depends on which basis I pick for them. So if I pick a basis where both orderings are the same, I have some kernel. I have only one independent because I have 4 points, so there is n minus 3 factorial, it's just 1 factorial, just one independent. And it depends on some external kinematics. So Sij's is just this Mandelstam invariance built in this way. And then you have some signs and some signs. There's a neat way to understand why the signs have to be here, and it's because the interpretation of this is an exchanging closed string states. Or if you're going to the field theory, you're exchanging some gravitons. And here you're multiplying two functions where you're exchanging gluons. So there's too many poles here. For example, there's a factorization when 1 and 2 get collinear together, and that will give you a pole of 2 higher order to be a gravitational amplitude. But one of those signs, S12, will get rid of that particular one, and it will lower the order of the divergence, so you get the right factorization to be a gravitational amplitude. So That's why you get the sines and cosines. And you get sines and cosines because they're string amplitudes, so you actually are exchanging an infinite number of states. So there's an infinite number of poles that you have to have this cancellation happen. Once you go to higher points, then you can pick a different basis as I pick here. The 5 points are string independent ones, and you get some other factors that also depend on this Mandel's time. So yeah, so what you get out of here is that this KLT is just really this bilinear on the open string amplitude, and this bilinear depend on external kinematics in this particular way. So those are the two interesting, well, for this talk, interesting relation between free-level string amplitudes.
And just to make sure, they got that H in closed form for all.
There's an algorithm to calculate on closed form. It is actually complicated. Actually, the more efficient one is the one using this twisted cohomology. That's the last one. Okay, so why is it, one of the reasons what I am interested in is that there is this relation, there's two things, in field theory, there's one thing that is known as color kinematic zoology, and associated with that there's a double problem. What is the statement of them in field theory? The statement of them in field theory is that if you take the low energy limit of the open string, so that's a gauge theory amplitude, so that's field theory limit here. You can rearrange it in terms of trivalent graphs. So this is a sum of the trivalent graphs. So graphs that look like this. And each graph comes with some C, which is a color factor, which is basically just a trace of the color matrix of these particles around here. And N is some kinematical factor that comes from everything that is not a propagator that comes here. So polarization, momenta, and other things. So there's a statement that if I can organize my amplitudes in this way, and to do that, you need to use a bit of some tricks, because if you were to calculate, for example, 4-point gauge amplitude in field theory, you have diagrams like this, which are exchanged, but you also have a contact diagram from the 4-point, and you have to open up this contact diagram into trivalent graphs. And you have to do that once you go to higher number of particles. You have to do that more and more times, and there are many different ways of doing that. But turns out that there is always a way of doing that, so you can always write the amplitude in this form. Moreover, it's been shown that for tree-level amplitudes, so when you have only trees, these kinematic factors obey a very interesting identity, which looks just like this the color identity. So this is so these are color matrices. So when you translate this back into FABs, FABCs, so for the algebra, the structure concepts of the algebra, you can show that there are graphs here which are related by this identity, which are related. There are trivalent graphs which their coefficients obey this identity due to the Jacobi identity. And what you can show is that at tree level you can always rewrite the kinematic factors to obey the same identity as the Jacobi. So there's no understanding of this in terms of a Lagrangian. This is really something that was observed and was proved later on to be true that you can do that. These coefficients are actually quite non-local from the space-time point of view, but it is a fact that you can do that. More importantly, if you take this amplitude and you take out these color factors and you put in some kinematic factors that obey this identity back in, and you end up with an expression like this. So a sum over trivalent graphs, some propagators for the graphs, and two sets of kinematic factors. Turns out that this is a gravitational amplitude. And so that's a non-trivial fact, but it has been proved at tree level that that's true, and that's what people call the double copy. So it's a way of getting gravitational amplitudes out of gauge amplitudes by this procedure. And the whole heart of this procedure is that the difficulty really is finding these numerators that obey this relation. And so how do you do that? You do that by using this BCJ, what I said before, this BCJ identities from before, that comes from these monodromy relations from this string. So there is a way of, one of the ways that you can prove this, so you can show this, is by starting with the string theory, starting with KLT and the monodromy relations, and taking the field theory limit, And then you can reorganize this field theory limit in this way to show, and you use KLT to show that this is true. Right. This is not the way that was originally done by the amplitudes community when they proved that. They proved it in a more complicated way, but this is the way that I think about it. That's really coming from the string theory, from that.
Is there a theory that looks like this but with two C's?
Yes, that's they call it like the double, yeah, the biojoint scale. Yes, so you can do that. But I don't know any string theory that gives a biojoint scalar as amplitudes, for example. Yeah, so this is all a tree-level story. You can write the same kind of decomposition on loop level, and then things become more complicated. It becomes more complicated because these identities don't have to hold up to 0. They can hold up to something that integrates to 0 when you integrate momenta out. So they're not algebraic in that sense because they have all that freedom that is difficult to take into account. Moreover, there is no proof that this is true. It just has been observed that every single time that we come up with some loop level amplitude, and in some kind of gauge theory like this, and we do this procedure, we always get some kind of route. There's a whole list. There is a review that appeared, I think, like a month ago, where there's a huge table of examples of where this is true. There's no first principle proof that this is always true. There's a lot of evidence that this is true.
How, you just said that the ends are difficult to find, the ones that sum to 0.
Yeah.
So it sounds even harder now. So how do you show this? Like, are you showing this based on explicit construction?
So what you show is that, yeah, so you start with an ansatz, and there are several different ways people do it, but people start with an ansatz where this is not valid, and then they recursively iterate that to try to make it valid. And then they square it. So you can do that at one loop, it's fine. 2 loops. 3 loops you put in a computer, 4 loops you put in a computer, 5 loops, people try, then you need even 4 loops you might need a supercomputer. So what people have done, the highest they've done is like Z's group and some other people. They found this 5 loop n equals 8 supergravity amplitudes, and that's the way they go about constructing them and calculating them. But they need to first construct an ansatz in gauge theory, and that takes a lot of time and it's complicated. But you do need to put in a supercomputer to do more than that. It takes some time. So yeah, if you were to find some way of getting this kind of identities for free, and that they get 0, you don't have to correct them, and then make life easier for them, but also will probably be a way of proving this things. Okay, so this is just going back to the Monodromy relations. So those things that I was talking about, they all come from the lower energy limit of the string. So like going back to the string, the way that the KLT and Monodromy relations were really derived first was really by doing, as I was saying, counter deformations. And what happens, as I explained in words before, is that you analytically continue the combination. Before you had the mod, so you take out the mod and analytically continue. This is a multi-valued function, because these are generically not integers. And you do these counter deformations, and if you're careful about branch cuts and everything, you find that you pick up a bunch of phases like that. And the origin is really because of this multi-valued this function. So you can sit down and you can look at papers, and it's a bit complicated at 3 level, but it's doable. But once you start to try to do the same tricks at higher genus, it becomes actually quite cumbersome. There's a lot of ambiguities. It's not exactly easy doing this counter deformation. It's not exactly clear what kind of space you're dealing with. So we wanted to do something a bit more clever. And by a bit more clever is really what I said before, using this theory of this homology, which was set up at 3 level by Sebastian, to higher genus. So what is this theory, and why is interesting? Well, why is it useful for us? So if you consider some, like, for example, some function which is multivalued, so we have z to be s, this s is some non-integer. You put some range cut along the real negative axis here. So this function is defined on some multi-shaded Riemann surface. But I don't want to work on this multi-shifted Riemann surface. I want to work in the original surface. In particular, I want to give a meaning to this kind of integral where gamma can be any path on this, even going across this branch cut, doing a bunch of crazy things. But I want to give a meaning to what this means. And so how do we? And this is nothing new. This has been work on this area for quite some time. There's a couple of textbooks which are quite nice on this. And let me explain. So what does it mean? It means so we have a function which is branch cut coming along here. So this is how we on the infinitely shifted Riemann surface. And let's say I want to define this integral between the 2 and the 1, and I want to define it such that it goes all the way down and all the way up. And I want to define it in such a way that the integral along all of this is the same as just the integral between the 2 and the 1. I want it to be homology invariant. So what do we do? So what I say is that, okay, you pick some particular, you choose what is going to be your initial branch, and all the other ones are going to be defined from that one. But what do I mean is, I mean that if I break this path in this way, and so I have one before the branch and after the branch, then there is, I define gamma 1 without any phase, as because I cross the branch, then this picks up the monodromy for gamma 2, there's a monodromy here for gamma 2 prime, and then you go back and there's no monodromy. So this one, if I now deform this counter here in such a way that it closes down, these two counters now they differ by a phase. By my definition, they differ by a phase, and then the space comes out in front. And then you see that gamma 2, gamma d, gamma 2 prime, then it's just closed, so you can close it down, it gives 0. And this one is also just closed up here, and you can deform all the way back to just be a counter between Z2 and Z1 in the usual way without any phase. So in this sense, it's an homology invariant definition, if you will accept. So it's really just a very basic idea is that if I cross a branch, I have to take into account that I cross the branch I got, so which means I just get multiplied, my counter just get multiplied by a phase. It's really nothing more than that. But this does then allows us to work on the original space, and there's a bunch of nice mathematical results you can use, which I'll get to later. But the example I want to give them now is.
So if you go back,
yeah.
So you're trying to see that if you just went from Z1 to X, that you would just get a phase.
No, that's how I define it. So what I want to define is I want to define some homology in such a way that if I do this kind of counter here, I can, this counter is homologous to just a counter from Z1 to Z2.
Yeah.
Right? And the way that I do is by basically saying that, oh, if I want to integrate this function all the way down to this point without a phase, then this next piece, by hand I put a phase and then I integrate it down. Yeah. And then I do the same thing as I go back, I cross back the counter, I take the phase out, and then I finish off here.
Z2.
Oh, sorry, yeah, I finish it. So I start at Z1, go all the way, get a phase, lose the phase, finish it.
Well, it's the same phase for going back over the branch?
No, I lose the phase as I go back. So this has this phase, and he keeps the phase as it goes here, and he keeps the phase, loses the phase. Right? So in that sense, I'm saying that I'm going to work, I'm not working on this, on the covert like this, I'm really working on the base space.
And what do I conclude for the second one?
So the second one is just saying that this is homologous to a counter from Z1 to Z2. So because I can close this, I can bring these 2 points together. So that's equivalent to having this, I add this piece and this piece here. Yeah. So gamma 1 doesn't have a phase by my definition. Gamma d has a phase.
But you just jump across and just get that phase.
Yeah, it's literally just that. You jump across, you get a phase. And just tells you that then this you can deform to 0, and this you can deform to Z1 to 0. It's just that. It's just saying that it's consistent.
So aren't you counting how often you cross the branch cut somewhere?
Yes. So
because when you would go the other way around, you would keep the phase, right? Because you are not
So if I had a counter which I go 1, 2, 3, 4, I will just keep getting phases and phases and phases and phases. So I'm going to get to what are the actual cycles in this homology in a second, and maybe they'll become clear once I get to what I mean by a cycle in this homology. But I want to do it in this framework of this, what I call the in the string theory. So again, this is an open string again, And what I'm going to do, I'm going to analytically continue. I'm going to keep 2 to n fixed, and I'm going to analytically continue 1. So this is the function that I'm analytically continue, and it's important that it has this ordering because if I exchange z and I pick some phase. So it's important that I started with this function. I'm calling t0, which is called a loading function in the literature, and that's what I start. This is multivalued, and it has this monodromy is alpha 1, which is just, as you go around each point, it picks 2 pi I k1 of k2. Right? So here, this should be a sphere, so there's some point in infinity somewhere through the blackboard. There chooses n fixed points, and I choose to pick these branch cuts. I'll start with Z2 and ending at some point, right? So alpha 3, as I said before, is Z1 going around Z3, so it picks up at each of the 2 pi I k1 of k3. Same thing here, same thing here, same thing here. Here, if it goes in this way, it picks all of the phases, but by momentum conservation, that just turned out to be the phase for k2, because it picks up the phases from k3 to k4, k3 to kn. Momentum conservation is k1 and k2. K1 squared is always an integer for the string, and so this goes away, so you have only k2. So this is my choice of branch cuts. You can choose other. This is immaterial in the sense that things are not going to depend on my choice at the end of the day, but you have to make that choice. So if I make this choice, then okay, so let's try to define what I mean by what is a chain, what is a boundary operator in homology. So as I said before, I can start at some point, so let's say point A, and go around to point B. I cross the branch cut, so I get multiplied by some monodromy. So mathematically, what is happening is that this chain it carries with itself a section of some line bundle. That line bundle, the monodromies are some endomorphisms of this line bundle. They are some just non-zero complex number. This line bundle is just C, so the monodromy is just homomorphism is just multiplying this section. So which means that basically in this case it just means that as gamma crosses, it gets multiplied by the monodromy. And I define some boundary operator with this, which keeps track of this monodromy, right? Because I started at A without any monodromy, so that's one of the boundaries, and the other boundary is B, but to get to B, I cross the branch cut, so I get multiplied by some monodromy. So these are 0 cycles on this complex, and they also carry some section of the line bundles. This is what it means. In particular, you see that if I close this circle, A and B are the same, this is not 0 unless the alpha is 1. Right? So a circle around is not a cycle in the explicit homology, although it is a cycle in the usual homology. So things change. And interesting now, then, I think they're interesting when I look at this kind of cycle. So if I look at the cycle that goes between Zi and Zi plus 1, this is the cycle that a string amplitude will be integrated on because you're integrating Z1 between 2 points. So this is the physical cycle for the string amplitude. This is also a cycle for the twisted homology because I'm not crossing any branch cut. Right? So the boundary of this guy is just 0. But this two, this circle, and this line, so this whole thing where I have this gamma 1 plus 1 in a row, it is also a cycle of this homology. And you can convince yourselves that if I do this combination of gamma 1 divided by this factor of the monodromy minus 1, gamma 1 plus 1, again, this monodromy minus 1, because this monodromy minus 1 is the boundary of the circle, and then rho because it's the boundary of those 2 points, then this combination here has no boundary in the way to define. So it is a valid cycle in the homology.
Why is it a cycle or not? It looks like it has the endpoints of the function.
No, not this one. Okay, so that's so this is a cycle in the there is a locally finite and not homology. So if I take the locally finite homology where I allow my samples to end up on the points, then they're fine. So in the locally finite, then this is a cycle, this is also a cycle. And in particular, there's a one-to-one map between this kind of cycles and this cycles. So you can map between them. You can use either of them as basis. So this in a sense, this gives a regularization of string amplitudes because you're taking a cycle which can be divergent and you're mapping one-to-one into something that is not divergent. It explains that. This is, if you know about, there's a way to regularize the string amplitudes using Poker contra. This is essentially the same if you understand. There's a way of getting this from the Bochner content. So that's what you gain from the Swiss homology, that things where you thought was on the base, things where you thought about where valid counters are not valid the counters anymore, but you need some other interesting things out of this. So in particular now, what I can say is that, so this is the notation for the first homology group with values on this line bundle. So this is the tracer homology, as I said. This is just a sphere with n-1 point fix. So the monodromy relations that I showed a couple of slides ago, then they turn out to be just a statement about the boundary relations on this group. And I'm going to show it. So this is what I'm going to show in a second. Moreover, the KLT relations, they come from a bilinear pair of this group. So these are so you can think about an intersection, just like you do the usual intersection numbers between between homologies. But these intersection numbers now carry this information about this line bundle. So there's a way of defining them, these intersection numbers. And it turns out that the intersection matrix for this homology is the KL3 matrix. And this was also shown by Izera a couple of years ago. And in particular, that is the geometric way of defining the KL3 matrix gives you different ways and more nicer, more practical ways of actually calculating what the KL3 matrix is. So this is what you got on that. And so let's show what this is. So I'm not going to talk much more about KLT until the very end, and we're going to talk more about this three level monodromy relations. So as I showed before, I had this is again my sphere with the n, Z2, Z3, amplitude Zn fixed. Z1 is moving around. Here I have again the same choice of branch cuts moving around. And I have this choice of contours that go between the points. So when Z goes from, so Z1, when Z1 is less than Z2, then you have a particular amplitude, that 1 is here. 1 is between 2 and 3, then the physical contour is this one. 1 is between 3 and 4, then the physical contour is this one, so on and so forth. And I drew in here in green, I have two boundary, I have two closed, two circles without two elements which are total boundaries on the homology. By that I mean is that simplest is easy to see. So imagine I'm just going around the equator, all around the equator, all the way to infinity and back, below this line, because this line joins itself at infinity. And then that's just there's no branch cut there, so now I just close and just give me one relation and give me precisely this relation here, as you would expect. So you have this relation you also have in the usual homology. But you get also an extra relation, which is this one, which has a bunch of monodromies, a bunch of coefficients that comes from this other counter, which is also closed on this tracer homology. And it is closed exactly because this guy starts with no phase, pick a bunch of phases, and then it starts losing phases as it goes out here, and then it doesn't have a phase anymore. So it doesn't have so it's a total boundary to the homology. This gives a more complicated relation like this. Of course, how I pick my contours is going to tell me how this relation looks, so it's up to me. But I pick exactly in this way to make one always simpler and another one a bit more complicated. The other thing you can easily see is that you can do a calculation, just by triangulation if you wish, to show that there are n-3 independent D counters, so these D counters here, which are in the tracer homology. And while in the usual homology, you only have n-2 independent counters. And that's really because in usual homology, you only have this counter as an independent relation. And this one doesn't give you anything new. While because here we really are taking, because here we're talking about this multivariate function with branch cuts, this gives you another different independent relation, then this number drops down to n-3. So from those two, what I need to do is now, so this one I said is the physical contour, but it's not the physical contour necessarily related to the particular choice of Copenhagen. As I said, the Copenhagen, if you remember back, it comes with some absolute values, but there are some places in this contour where this becomes negative, so that's not what we want. So do you want to rewrite this in terms that it's manifestly positive, so you can put back the absolute values, that gives you some extra phases that come out in front, so it just they comes out in front, and so it's just saying that once I integrate this over the quantity I, which is 1 between I and I plus 1, I get this amplitude, which is with this phase that comes from just changing the order of these guys. And this gives you the physical amplitude, that's what I call the physical branch. And then by doing that, from this ones, you just, from this relation of the homology, you extract this relation between these three amplitudes, which are the monodromy relations that we had before. So, and it comes out of that. And so now this number n minus 3 factorial just comes from the dimension of this homology group on the full modular space. So that's just a simple argument that I think so slightly behind schedule. You can ask me about it later how to get it. But this doesn't involve any kind of permutation or any other argument. It's just a topological argument about some Euler characteristic of this manifold. And you get for free by doing this. So just quickly, that this framework of the space homology has other applications. So you can explain some of these CHY formulas and which is strings formulas. This formula which has also been discussing equations. These localization formulas have an interpretation in terms of intersection numbers of these homologies. You can ask me about this later and we can talk about it. There's also some application of the same framework to talk about honest Feynman integrals that people are interested in. You can use them to you can rewrite Feynman integrals in this way where you have something that is multi-valued, and then you can use these arguments to find a basis, a minimal basis of Feynman integrals. You can find differential equations for them using this framework, which is quite interesting. And there's also some localization formulas in the literature that you can interpret them as also some kind of intersection theory, and then you can use all of this framework again to find basis, projections, scale, analogs of KLT and that kind of stuff to this, which is, you can ask me about later, but it's quite recent work and it's quite interesting. What I'm going to talk about is a little bit of some generalization that then I did with Piotr and Sebastian to finish off is just then how do you generalize this to loop level? And generalize this to loop level in string theory means working in high original surfaces, or in this case, because it's the open string, I have more boundaries. So I have here the annulus, so this is a one loop open string, so I have an annulus, so there's two boundaries, one that is denoted by this green line, the other one denoted by this red line. I'm only going to talk about gauge theory amplitude, so all my punctures are on the boundaries. There's no puncture in the middle of this annulus. In particular, and the other thing I'm going to do is that I'm going to pick a particular representative of this A cycle to measure the loop momenta through. So that means is that I'm adding by hand this loop momentum, which in the string theory is not there, but it is essential to make the story work, and I can explain later why. And it also makes taking the field theory limit much simpler once you have explicit loop momentum. And by that I mean that when I write down this is not the amplitude, this should be the integral, because this depends on the L. So I have an integral over the modular parameter, which I'm not going to mess around, so we're just going to keep it fixed, basically. An integral over the configuration space, so this configuration space is just two permutations along the two boundaries. I have, again, the function here, which is just some polynomial on L, and it's just some rational functions on the Z's. This doesn't have any branch cuts on Z, so this is basically non-universal, depends on the theory. Then the universal piece, which is the analogous of the Copenhagen, is this piece here, which has an analogous of the propagator Z1 minus Z2, which is given by these theta functions. Which is, you don't need to, the only thing you need to know is that these guys behave locally. So for Zi equals to Zj, it behaves like Zi minus Zj. So it has the same local monodromies as the tree level. And it has these extra phases that comes from basically zero modes, which I trade off by explicitly dependence on the loop momenta. So this is an L squared, and I have this extra phase with the loop momenta here. So in particular, so that is the thing that I want to continue. So this is my loading function for one loop. And again, here you have the part which looks like, you need to put this because of the mods, so just some normalization. But theta 1 and theta 2 are going to behave, as I said before, just behave like z1 minus z2 when z1 and z2 is closed. So this have the same monodromies as that piece. The new piece is this phase that has monodromies once you go along the A in these cycles. So effectively, this function here then doesn't live on this annulus anymore, it lives on this torus. And the way to see it is that basically, maybe what you see the other way around is that you start with this torus, you have one, you draw this green line around these punctures, the red line around the other punctures, so you have these two cycles, and then you project in such a way that you keep fixed both these cycles, this two projection, and then you recover the open string worksheet. But this one, we want to go the other way around. We want to analytically continue the open string integrand in such a way that it makes sense on this surface. And again, as I said before, I choose this cycle to measure the loop momenta, which means I choose this cycle to measure the loop momenta as I go around.
This step was not there before at tree level.
It was there.
It was.
Yes, you know, it was. I didn't. I should have put it in slide. It's here, right? Because this is the actual moduli space is sitting here. The integration is going to sit here. I analytically continue, and it turns out that by momentum conservation, this analytical continuation actually does live on this sphere. It's not only on the plane. It does live on the sphere. So, and this step is here. But the thing is that here I'm lying a little bit to you because the loop momenta is different between those two sides. So if I measure the loop momenta as coming from this side and coming from the other side, it's different. So, which means that actually what I'm working with is in a cut surface where I cut along this A cycle here because I introduced this loop momenta. And there's a reason why I did it, and it makes things easier. But that's the. At the end of the day, I can always identify them, but I will choose not to for reasons I'll come to later. So now if I open up this torus in the way that I said before, then you have this is the green, this is the blue line from before, this one around here, and then I pick this other red to open up this way. So B cycles here at H5, and this is the A cycles here. Well, in the middle of what I said by green, which was the D's from before, is on this axis of symmetry here. And very much analogous to tree level, I have these local monodromies, which are the same. It just comes from going around Z1, going around ZG. And I have these other monodromies that comes from when you move between along the A cycles, that you pick some loop momenta, and you pick also this guy because I fix one point at 0. But you can do other gauge fixings and get slightly different things. The red lines again denote a choice of branches. So this is a choice of branch cuts. And to make matters easy, I choose all of them to lie in one side and the other one to have no branch cuts. And just as before, I do two boundaries, two contours which are total boundaries in the homology. This is simple. This is just the same as before. I have this one which doesn't look like it's a total boundary, but if you go through the details, you see that it's a total boundary. And that gives you two relations. There's a simple relation like before. You have this D contours, which is one boundary. B contours is the other boundary. Then you have these contributions between A and C, which are these contributions along here, which were not there before. These are not physical string theory contours that they had before, but they are here on the relations. You have this more complicated one, which is basically the same thing as before. You have to do the same procedure as before of projecting this down into what we call the physical branch, which is just you have to slightly change this function to get the actual physical string integrand on each cycle. That just gives some extra phases. You go through it, and you find some relations like this as before. So let me unpack this a little bit. As I had before, 1 started before 2, and as it moves through, it just picks up phases, k1 of kj, as it moves through ij, as to j. Once it changes the boundary, it goes through that I cycle, it picks up a loop momenta, and then keeps up picking local monodromies as it goes through. The new thing is that this is not equal to 0 like it was at tree level, but it's equal to those two things that I denoted by j's. Those are counters that go along the A cycle that I had before. Those are counters that go along this guy from this side and from that side, from slightly before and slightly below. they don't cancel because they have different phases, and they are there in their relation. So those are not physical string amplitudes. I don't know yet the interpretation of them in terms of string amplitudes, but they have an interesting field theory limit, and it's very interesting field theory limit, which I'll talk about soon. So these relations were already there in the literature, Copenhagen, Stieberger, and Turkin and Van Hove, although those two disagreed exactly on what they were. And we solved that. We just said that this is the correct one, there is this phase, we cannot just cancel. They thought you can always cancel these guys, and we said that that's not true, because they have different phases. Also, they did checks to low values of alpha prime expanding. We did a numerical check to generic alpha prime to find that this is always true. We did check up to n equals 9 particles in both problems. So we're very confident that this is true. So to higher loops, you can do something very similar. Now, I'm not going to write everything, but just the universal part of the string theory integrand is, again, this is the prime form, which is, again, it's just a generalization to higher genus of Zi minus J. So it behaves like Zi minus J when Zi and J are close together. In particular, it has the same local monodromies as each of the 2 pi I here at Kj. And you have, again, the extra phase that comes, that depends on the loop momenta, and now we have, which is integrating some abelian differentials. So the details are not, you can ask me about the details later, but the important part is that this has the same local monodromies as 3 level, and here you have some extra monodromies along the A cycles, and these cycles are taken from these guys. So I use this as my loading function, where I put particles. This is just to denote that I'm putting particles. This is when they are in the same boundary. This is when they differ by some, they are in different boundaries, they differ by some fraction of the A cycle, so just a heuristic notation to how to write this down. And which basically is just means that I started with this, the worksheet that I had before, partial higher genus, in this case. More boundaries is that I have a boundary around, which again is like green. I have a bunch of P cycles that I don't know, which are these boundaries in interior with a bunch of particles. And it's important that I measure the loop momenta along the A cycles where they meet at a point, like this. And then as before, I can undo the Z2 projection to get that function defined on a higher genus surface. And essentially, this is what you get. You get this surface which is cut along the 8 cycles. So I'm cutting the surface along these cycles and cutting the surface along this red cycles along here. This is again, this is the new boundary, so when I do the projection. Another way of thinking about it is if I don't cut those red cycles, the P cycles are just keeping like that, I just open up the A cycles, and that's how we measure the loop momenta going around. So in particular, is in this surface that I have to define my branch cuts, and like this light green is where I'm going to define the 2 independent relations. So working on this, it might seem a bit complicated, but what you actually do is you open this up on a plane, and this is the figure you get, which the first look, it's a bit complicated, but it's not, as once you understand. There is this axis of symmetry, which is the green boundary that we had before for the multi-annulus. I have a bunch of B cycles here that are identified from on this side and on this side. Again, a B cycle, B cycle, B cycle, and B cycle. You have those A cycles in blue that goes between, and then you go around and go back to this boundary, as we had before here. You go here, go around, and go back. So this drawing is literally just opening up that into on the plane. Again, I have my choice of branch cuts to take out the monodromies of the multivariate integrand. And I define 2 counters which are 0 in the homology in this way. Out of them, then I get, again, there's something which is simple because it's on the side with no branch cuts, something more complicated on the side with branch cuts. Again, as I said, the monodromies are the same as before. And from this 2, you do the same procedure as I did before, and you get these monodromy relations, which are just generalization of what we had before. And again, once one starts from here, as it goes around, it picks up some local monodromies, K1 of Kj, as it goes around. As it jumps to a new boundary, it picks some local momenta, so every time it goes to a new boundary, it picks some phase depending on new phase depending on local momenta, and keeps picking phases, local phases from the particles, and goes through all the boundaries until it comes back to itself. And on the other side, you have all these cycles that goes along the A cycle that they don't cancel, and they have some particular phases we found out. And we can see that even at higher genus, they're never going to cancel just that. And these are the higher genus monodromy regulations that we get out of this. So we can count the number of independent relations out of this. This comes because, for reasons which you can get later, that this cohomology of local systems, it localizes to the middle dimensional cohomology. There's only one cohomology group that is non-zero on the moduli space. So if you calculate the Euler characteristic of the space, it just gives me the dimension of the moduli space directly. Just to say it, then that's how I get the n-3 factorial for genus 0. I get n-1 factorial, and then we can go back to the relations I say. You really see that I get this number is matches what we got for genus 1, and there's some generalization for higher genus. But these numbers are slightly, for higher genus, they're slightly too big, and they're slightly too big because one thing that I didn't take into account is that there is a symmetry that my setup doesn't know about, which is this Z2 symmetry between this side and this side. So it's treating some counters here as different from this side, but they integrate to the same thing. They give it the same amplitude. So if you take into account that Z2, then the number drops down to this one, which is which is the natural generalization from genus 0, when you take into account that Z2 symmetry out of this. And comparing to this just gives you a little bit better than if you were just counting the number of independent amplitudes by a naive counting, just putting particle amount about this. So just gonna like 5 minutes and talk about why I set up, what do I gain by doing all of this. And I gain is by taking the field theory limit of these relations. So the field theory limit of these relations, they look something like this. There is a string integrand that depends on alpha prime. It has some phase depending on alpha prime. And you get always two relations out of this. If you look at the order 1 terms and the order alpha prime terms, always gives you two relations for the field theory amplitudes. So as far as you can tell, we can rederive all the relations that people knew for integrands from our relations. They are a bit more general, but we can certainly rederive things that people knew using them. But more importantly, the way that we set up and why we had this fixed loop momenta means that our relations, and this side is really 0. You never have to worry about doing a shift in loop momenta to see that these relations hold. These relations don't hold up to integrations of the loop momenta. They hold, period. They give 0. So that's how we can do these checks numerically, is because we can just put it in a computer and see if you get 0 or not. We don't have to worry about these things. And so that's what gives you more power. That's what makes these relations more powerful, is really because you can check them for fixed loop momenta, and moreover, the definition of the loop momenta for the string integrand gives you a canonical definition of loop momenta for all the graphs that come from that string integrand. So that's why it's interesting. Moreover, I talked a little bit very quickly about these J cycles, which are the cycles along the A cycles, that they don't correspond to anything physical in the string. And what you can see is that this guy actually contributes some contact terms. So as I was explaining before, that this usual amplitude just gives you these trivalent graphs, but when I take the field theory limit of this amplitude where I have this particle going around this edge, this gives me something like this gives me something like this. So it gives me some insertion of some contact terms over here. So they have a life in the field theory limit, and actually a very important life to make sure that these relations actually work on the nodes without having to shift to the momenta. So basically you can throw this out, but if you throw this out, then the relations hold only up to shifts and loop momenta. And that's interesting. One of the things that is interesting for us is that because now this gives a a canonical way of defining loop level BCJ relations. So as I said before, BCJ relations are written in terms of these three-valent graphs for tree level, but also for loop level. Loop level, they will look something like this, where you have this kinematics in front of each of these three graphs that they have to obey. And 1 and 2 and 3 have to sum up to 0. But the usual way people do it is that they sum up to 0 up to the shifts in loop momenta. But if we track down how these things comes from the string, we can give a relation that they should obey on the nodes without having to shift the zero momenta. So that makes these constructions of gravity integrants very much more simpler, I hope. We're still looking into that, into how to get this, because systemizing this filter limit is a bit messy, but we're looking into that. And yeah, and these guys also have some other, it's not only, they have other interesting contributions, not only these contributions from that. And moreover, what I hope, also another thing about this project is that we can use what you know to actually prove that this double copy is true. Not only show that we can do this and have this color kinematics explicit, but show that the double copy in KLT is true. In particular, you want to show that at some points that KLT exists at loop level and exists as an intersection of this homology we define at higher genes, right? So just this last slide, just to say what we did is so we generalized this homology to higher genus in a particular way, and we found out that monodromy relations are boundary relations with homology. We found some nice interpretations for non-physical contours in the field theory limit. And things we are working on now, it's just really, as I said, to systematize this field theory limit to find these new relations. Understand a little bit better this counting that I did, which is a bit fast, and I can tell you why later on, that these kinds are independent contours. And more interesting is really, now, what I did is really just on a fiber because I fixed all the points and I moved only one particle. So I want to understand how to do this for the whole configuration space such that I can now define KLT as really intersection of this whole configuration space. And you can ask me about that later. That's it. Thank you.
Do you have any questions?
You? So the loop momentum that you introduced, the big one,
Yes.
is this essentially keeping track of all monodromies across all the branch tests that you could have had, or what's
It's thinking. So there is a particular way. It's because